So if I look at a simple example here, sort of like what I've just done, if I've got a pure shear force acting on that of load P, I have a cross-sectional area, if I assume this is repeated over there. If this is length L, I've got a weld bead of H, then the area is 0.707 times H times L times 2, because it's both sides. So then my primary shear is simply going to be P divided by 0.707 HL times 2. Okay, so that's fairly straightforward, which is what I've just done. We won't go any further. If I have a look at another example, primary shear on a butt weld. So let's have a look at two 17mm thick plates with a yield stress of 425, butt welded. I don't think I've mentioned real much about E70 welding rods. E60, 70, 80, 90, they're the strength, nominal strength in PSI or KSI, thousands of pounds per square inch. So it's an American nomenclature. I will put up in Canvas a CIG reference document. Just for curiosity, you can see all the different sorts of welding consumables that there are. But again, E70, you can just look that up in Shigley. It'll tell you what its equivalent yield strength is. The weld length is 90. What is the maximum tensile load with a factor of safety of 4? Okay, so this permissible stress is 0.58, which is 0.577 rounded up, times 425. So I'm allowed to have, in that sense, 246 megapascals. Primary shear, stress, force over area. Area is T times L. T is 0.707 times the weld height, if you're given it in that direction or that way around. So we can work out that we can get 94.1 kilonewtons sitting on that plate. As compared to an unwelded section, well, 17 by 90 by 425 is 650 kilonewtons. Give that a factor of safety 4 and we get 162. So there's a factor of safety inherent in this thing of 1.72. So this is going to allow for, everything that goes with the weldment, basically. So if this is a weld that, is un-X-rayed but done by a professional, then this is probably the value you'd be assigning as a suitable load for it. You wouldn't be going anywhere near this. So again, I believe these are pre-qualified levels that you can use. If in doubt, check your standard. Everywhere, check your standard. We have what's called secondary shear or torsion, because never do we just put a pure shear on. It's almost impossible to put a pure shear onto something. So if I put a load out here, that equates to a pure shear as well as a moment acting about the centroid of the group. Okay, so what we've got to do is deconstruct that value of P or force, whatever, into a pure shear and a secondary shear. And so what we need to do is work out where the centroid is of our weld groups, right, to work out effectively what our J is, polar moment of inertia. And we add the primary shear to the secondary shear to get the total shear. Now, this secondary shear will be different in different directions. So one of these will carry more load, will be the point where it fails first compared to the other one. So what we're going to do is we assume that the stress is proportional to the distance away from the centre of gravity or the centroid, which means this point here is going to have the highest stress level of the lot. You can go through the math, work out, how to work out the centre of gravity. Again, it's just a parallel axis type theorem. We can go through and show that shear stress over radius is a constant, and we end up with this equation, which is the important one. Since we assume the stress to vary directly with R, shear on R is constant, we use maximum torsional stress, maximum distance from the centroid, add them together, parallel axis theorem to find the J for the weld on an axis. So all of that we work through, and we can work out that J here is, J01, so there would be J01 plus area times the radius squared to work it all through. Now, one of the nice things for this is that if you think about the length of the weld versus the thickness of the weld, T is a lot less than L. So that sort of can simplify down so that your J is just AL squared on 12. So that makes it a little bit easier for us. Again, we can work that through to work out that our J0, there's the parallel axis theorem there, adding the JO1 to get to JO. We've got a radius, we've got an L, etc. So it's all fairly straightforward to work out the J. Now what you can do is, and what's easy enough to show, is that you can unitize it. So you can assume that the weld is just a line, because if you're trying to optimize it and you were having to work through the full dimensions of the weld, so the area, the length, the height, the throat thickness, and every time you changed you had to read all the calcs, and a bit of a pain in the backside. So you can show that using a simplification of just using a line as your weld, and then multiplying it back to give you the weld size is obviously a really nice, neat way to do that. So if we have a look at an example of that, I've got a tag welded onto a piece of something big and heavy and blue in this case. It's onto a significant structure, 5mm weld length, overlap 50mm, 10 kilonewtons, 250mm from the edge of the structure. Area, I can work out again from that table that was back a page, and it's just in Shigley if you look it up. Sorry, the numbers are a bit fuzzy in this scan, but you can work through that where your X is, which is somewhere about here. Clearly Y is simply in the middle, so at the centre line of that, and we can work out what J is, so that's all pretty nice and easy. Primary shear, 18.85 megapascals, woohoo, that's nice and strong. Let's have a look at the secondary shear, T times R divided by J. So the torque is 10,000 newtons. That's my distance, 250 from the outside edge, plus the 50mm overlap, minus the 16.6 where X bar is. The square root of those, so that's finding out where that maximum radius is, divided by J, and oh dear, it's 1000 MPa, so that's not going to do it. So we'd need to go back through, put a bigger section in or something. Just for noting, just a habit, write your units down as you're doing your sums. That way you can work out, and I've got Newton millimetres times millimetres, so that's Newton millimetres squared divided by millimetres to the fourth is Newton millimetres squared, so that's megapascals. Okay, so it just helps to give you that second check of what you're doing for yourself. Here is another welded joint. In this case, we've got a boomerang-shaped tag with a load hanging vertically from it. Put a 6mm fillet on each side of it. How strong or how big of the weld, or determine the maximum value of P such that the weld yield stress is 345 MPa, factor of safety of 2, standard sort of stuff. Work out the weld throat area. We can work out, based on the value of P, what the direct shear stress is, and we can work out that 253 kilonewtons we can hold on that thing. So that's pretty cool. What if, same bracket, same arrangement, let's say the job shop let the apprentice do the welding on one side, and they didn't do a real good job, and so they've come back over it and put a much bigger weld. Now, we're not going to worry about, whether it's a single pass or a triple pass or whatever. We're just going to assume it's one big fat weld now, for whatever reason. And so, is that good? Is it bad? Does it make no difference, I guess, is the question. So, we can go through that same sort of analysis. The left weld has this area, right weld has a much bigger area. So we've got a much bigger throat area, so that sounds useful, doesn't it? We've then got to work out where the centre of mass is for all of these big welds. And we find that it's 284.3. All right. So what this means is instead of to put this load here, it's equivalent to acting through here, but we also get a moment in the system because we're off centre. Okay. So we can go through and work out the left and right distances, and that's going to be from the centre here to the centre of the action, and from that one there. So for there we work out the value of J, because unlike the first example we had, where we had a weld around here, and this sort of made sense that we're putting a torque and we're putting shear in all of those welds, and that sort of is what your brain immediately thinks to. We're sort of doing the same thing here. We're putting a torque this way, which is adding to the tensile load on that guy here. But we use the same sort of process. So left weld, right weld, we get a J total. Our direct shear stress has gone down, I'd say. The moment arm, however, gives me this 53 millimetre or 52 millimetre amount here that we need to put a moment across. So we can calculate that, right? On this side it's acting downwards. We can add those together, equate it, and 233. So call it 234 kilonewtons. And that was versus 253 kilonewton with the 2 by 6 millimetres. So we've actually dropped load, all right? And we've dropped that load because moving the centre of mass offset puts more torsional load on that smaller weld. So, the first gut feeling of I've got more metal, it must be stronger, doesn't always work out. The next thing to consider is bending in welded connections. As I say, it's almost impossible to get a pure shear case. It's almost impossible to get a pure torsion case. There's always going to be some combination of loads, and bending is just another one of those. So again, we've got a piece of bar B by D welded onto something big and solid over here. Little fillet weld top and bottom. Again, the welding symbol is telling you weld this side with a fillet weld the other side with a fillet weld. Doesn't say anything at all about those two guys. All right? So we've got top and bottom welds. They've got a thickness. The primary shear is simply force over area. But then we've got a bending moment. And so we just assume that the stress there is my over I. Again, tables with unitised values. So it can be fairly quick to work out for common welded arrangements what your bending stress is going to be. So far all we've talked about is breaking the welds. But you can also have the problem where you rip the weld off the parent material basically. So your welding rods, and again I mentioned E70, yield strength 393, tensile strength 482. So if you're welding a bit of 250 MPa yield mild steel, then clearly your E70 electrode or your weld is a lot stronger than the parent material, and so you may end up ripping the weld off the parent, not breaking the weld at all. So you need to check your tearing stresses, and there you're just going to replace T with H, right, to make sure your stresses are okay. But it's also where it's important to use the right electrodes for the right jobs. So not only do we have differences in yield and ultimate, but you've also got variances in the elongation. So you want to make sure you've got the right amount, the right electrode for the job, I guess, is the important part.